So we talked about measuring the change in internal energy of a reaction at constant volume in the bomb calorimeter. It's also helpful to be able to look at things at constant pressure. And this happens when the reaction is open to the atmosphere. So the pressure of the reaction will be at constant pressure, which is equal to the atmospheric pressure. So in this situation, the energy involves Q, which is heat, and W, which is work. But usually we're only interested in the heat. We don't really care about the work. As the reaction expands, it may be doing work against the atmosphere, but we really don't care about that. It's not very useful. So we use a concept called enthalpy. Enthalpy got the letter H. The enthalpy is the sum of the internal energy of that system and the product of its pressure and volume. So enthalpy H equals E, the internal energy, that's the quantity we've been looking at, plus the pressure times the volume of the system. Now, like that equation is not very useful. But enthalpy is a state function, meaning that it matters where you start, it matters where you end, it doesn't matter how you get there. And so we can look at enthalpy change, and this is a very useful quantity. The enthalpy change is going to end up being equal to the heat evolved in a reaction at constant pressure. And so this is very useful, because this is how most reactions occur. If you light a Bunsen burner and you're interested in the heat evolved from the combustion of the gas, that is occurring at constant pressure, and so the change in enthalpy is something that you're interested in. So how does enthalpy end up equaling the heat evolved? Well, if we take the change in enthalpy is going to be equal to the change in the energy plus pressure times the change in volume. Okay, where we started was with H equals E plus PV on the previous slide. Now we're saying, as this reaction changes, we're saying that it's happening at constant pressure. So the pressure's not changing. That's why the pressure doesn't have a delta in front of it. So delta H is the change in internal energy plus the pressure times the change in volume. Well, we saw this P delta V thing earlier when we said that the work done, the pressure volume work, was equal to negative P delta V. And we also learned that delta E equals the heat plus the work. So we're taking this relationship and plugging it in here. Now we're giving Q a subscript P, indicating that this is the heat evolved at constant pressure. So the delta E, the change in internal energy for the system, is the heat evolved at constant pressure plus the work done against the atmosphere. And then plus P delta V. Now we're going to take this and substitute in this equation. Because if we change the sign, if we move the negative to the other side, P delta V is equal to negative W. So when we substitute that in here, we get Q at constant pressure plus W minus W, and we end up with the change in enthalpy being equal to the heat evolved by the reaction at constant pressure. I'm not going to test you on that derivation, but I think it's useful to see how we come up with these things, that we're not just pulling them out of thin air, even though it may appear that way sometimes. But here in the box is what we need to remember. Delta H is equal to the heat evolved at constant pressure. So even though delta H is not change in heat, it is related to heat, and so it being an H is useful. We have to try to remember there's a difference between delta H and delta E. Delta E is change in energy. Delta H is related to heat at constant pressure. H stands for enthalpy. Any questions yet? This is stuff that's kind of hard to keep straight. It really is. So, delta H and delta E are very similar in concept, and that's why they're hard to keep straight. And often their values are very similar as well. And so, if we treat them like they're exactly the same, are we going to get into big trouble? No, we're not. But there is a subtle and significant difference, and so we're going to try to remember the difference. And then if we don't, we'll just go on our merry way and we'll be okay. So delta E is a measure of all the energy exchanged with the surroundings. That's the heat and the work. Delta H measures only the heat exchanged under constant pressure. So they're very similar, but they're slightly different. For some reactions, there's no practical difference at all. The difference is largest when you have reactions that produce or use large quantities of gas, and therefore there's a large volume change. If the volume change is big, then delta H and delta E are going to be more different. When the volume change is very small, the difference doesn't matter much at all. So, exo and endothermic. Remember that endothermic, is the concept of going in. Thermic relates to heat or energy. So endothermic is energy or heat going in. Exo, like the exit, you're going out. So the energy is going out. So if delta H is positive, heat is being absorbed by the system. And we're keeping our sign convention here. Like with money, when money comes into my wallet, I have positive feelings about that. That's a positive experience for me. So for the reaction, when delta H, the change in enthalpy, which is equal to the heat at constant pressure, is positive, then heat is going in to the reaction. That's endothermic. And when delta H is negative, the heat is going out. When I have to pay someone money from my wallet, like when my son got his van towed, it was almost $500. That was a very negative experience, right? Money going out. Heat going out is negative, okay? Heat going out, exothermic, okay? We talked at the beginning of the chapter about chemical heat packs. Many of them have iron filings that get oxidized. This is an exothermic reaction. It releases heat. Heat is going out. This is an exothermic reaction. What would the sign on delta H be? Negative. Because we're taking the point of view of the reaction. You have to think like, okay, I'm the reaction. Is the heat leaving me or coming in? When we're using a chemical hand warmer, we are part of the surroundings. And we feel the heat coming to us, but it's coming out of the reaction. So delta H would be negative for that. Chemical cold packs do the opposite. Many of these contain ammonium nitrate, and when that dissolves in water, it's an endothermic process. Heat is absorbed by the reaction. And on the outside of the reaction, we feel that as absorbing heat from our hand or our, busted up knee or something, and we feel that as cold because energy is going into the reaction. That's an endothermic process, so delta H would be positive for that reaction. So what's going on the molecular level? Well, the exothermic reaction gives off thermal energy. That energy has to come from somewhere, right? It's not coming from the thermal energy of the chemicals. because if they were losing thermal energy, they would get colder, and that's not what happens. What happens is we've got some of this chemical potential energy that's stored in the reactants. And in the process of that reaction, some of that chemical potential energy is converted into kinetic energy in the form of heat. Remember that the total energy of something is its potential energy plus its kinetic energy. Okay, so chemicals have stored potential energy. So in the course of a reaction, we get bonds that were there to begin with get broken, new bonds are formed. Some of those are higher and lower in energy, and depending on their relative strength, we can have energy being given off or energy coming in. So in an exothermic reaction, we have the products having less potential energy than the reactants. And the difference in that potential energy is released as heat. Oh, I was hoping we had a little diagram. I'll make one. So this is energy. And so in an exothermic reaction, the reactants are higher in energy and the products are lower in energy. And this difference is what gets released as heat to the surroundings. That energy had to go somewhere. So the reactants had more potential energy and the products have less potential energy. The potential energy gets turned into thermal energy. What about endothermic reactions? Opposite process. The temperature of the surroundings drops because the system is absorbing thermal energy. And where is that thermal energy going? Well, in a reaction, we've still got these bonds being broken and formed. Now the products have more potential energy. The thermal energy that's being taken in from the surroundings, resulting in the system becoming colder, the kinetic energy, the thermal energy is now being converted into potential energy and being stored in those chemical bonds. So for an endothermic reaction, again with E here increasing, now we have the reactants down here and the products up here. And the products are higher in energy. They absorbed thermal energy from the surroundings and they converted it to potential energy. Basically, they're sitting on it, they're holding it. Okay, so exothermic, endothermic. So back to enthalpy, that capital H thing. The enthalpy change for a chemical reaction is indicated as delta H reaction. So change in enthalpy of the reaction. And we often just call that the enthalpy of reaction or the heat of reaction. Heat of reaction is easier to remember because it's a delta H, and so that makes us think of heat. And under constant pressure, it is the same as heat, and so we're kind of okay there. Enthalpy is an extensive property. Remember, intensive, extensive properties. We keep bringing those up. An intensive property is an intrinsic property, right? It's like density. It doesn't change with the size of the object. An extensive property depends on external things. It depends on the size. So enthalpy is an extensive property. The amount of heat transferred to or from the surroundings is going to depend on the amount, right? If you take one stick of dynamite and you blow it up, or if you take 100 sticks of dynamite and blow them up, there's a difference in the amount of energy that's given to the surroundings, right? It depends on how much you have. So enthalpy depends on the amount. So it needs to be specified. So the convention that we have is that we tie it to a chemical reaction, a chemical equation. And however the chemical equation is written, we're going to interpret these coefficients as molar quantities. So we're going to say 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. And for those amounts, the change in enthalpy, or the heat of reaction, is minus 2,044 kilojoules. Now, looking at the sign of this, is this an exothermic or endothermic reaction? Exo. Heat going out. Okay? So this becomes a conversion factor. And we can do stoichiometry and use energy as one end. How much energy would be generated if we burn this much stuff? Or how much energy is needed to do this thing? And so we make these conversion factors the same way we do between moles of this and moles of that. We would say 5 moles of oxygen produces 3 moles of carbon dioxide. We say that 1 mole of propane, because there's a 1 in front of this, we just don't write it because we don't like ones. 1 mole of that will equal this much energy. Or 5 moles of oxygen will release this much energy. So let's do an example. Ammonia reacts with oxygen according to the equation given here. And here's our enthalpy of reaction, our heat of reaction. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. Questions we've done before have been, okay, if you react 155 grams of ammonia, how many grams of water are produced? That's the sort of thing we've seen before. So we just have another little twist in our general stoichiometry path. Okay, normally it was grams to moles to moles to grams, right? That's our stoichiometry mantra. Grams to moles to moles to grams. Well, in this situation, we're starting with grams, but we're going to end up with kilojoules. So instead of going to grams at the end, we're going to kilojoules instead. We're going to take a right turn. Then the process is very much the same. So we're starting with 155 grams of ammonia. We've got 3 arrows. We're going to have 3 conversion factors. First, we have grams, then we go to moles of that quantity. Well, I didn't draw that very well. Let's think about this for a minute. This amount of kilojoules can be related to any of these. Do we need to convert from moles of ammonia to moles of anything else? No, we don't. So really, we can skip the last 2 steps, because we can relate kilojoules of energy directly to moles of ammonia. So then we're going to kilojoules here, and we're done. We put our units in. And we put grams in down here. And then we go looking for numbers. The number for this conversion factor comes from the equation. Here we have delta H reaction, the heat of reaction, is minus 906 kilojoules. So minus 906 goes in front of the kilojoules. And that much energy is released for every 4 moles of ammonia. So 4 goes down here. A little tweak on things that we've done before. And this is our old friend, the molar mass. So nitrogen, 1 nitrogen plus 3 hydrogens, and that gives us 17.034. And then, I forgot my calculator again. $155 divided by 17.034 times negative 906 divided by 4 equals, how many significant figures should our answer have? 3. So my calculator is showing me this. Always a good idea to write down what your calculator shows you. And we want 3 significant figures. That means we're stopping at the 6. It means we need to be careful. We can't round this to minus 206. That's changing the magnitude of the number, and that's not what happens when you round a number. We're rounding to the tens place. We should put this in scientific notation first. So the decimal point, remember, is getting moved 1, 2, 3 places. How do I know that's a positive 3? I remember that's a positive 3 because I look at this number, 2061. That's a large number. That's a big number, so the exponent's positive. If you have a small number like 0.0026 or something, then the exponent is a negative number. Because big paychecks are positive and small paychecks are negative, right? People understand money. Now we can round this off and we'll be just fine. Minus 2.06 times 10 to the third kilojoules. That is the heat associated with the complete reaction. Now, depending on how the question is worded, especially in mastering chemistry, they may or may not want the negative sign in the answer. If the question is, how much energy is released? Okay, we do this calculation, we come up with a negative heat. That is heat being released, right? So if we say how much heat is being released, the negative sign is implied in the statement. And so we're not going to say negative 2006 is, or 2060 is being released. We'll say 2060 is being released. So that gets a little confusing sometimes. I would recommend just always paying attention to that negative sign. Yeah, it looks weird to have a negative sign in your stoichiometry calculation, but if there's energy involved, it may very well be a negative. And then you can sort out whether the question wants your negative sign in its answer or not afterwards. So best to just keep the negatives where they belong. Any questions? So we talked about constant volume calorimetry. That was in that bomb calorimeter. We can also do constant pressure calorimetry, and this is what we usually do in general chemistry lab. And so here what we're doing is we're using what's often called a coffee cup calorimeter, because many times it literally is a coffee cup or 2 coffee cups. 2 coffee cups work better, but it's still coffee cups. Styrofoam cups. They work actually pretty well as calorimeters. Styrofoam, why do we drink coffee out of a styrofoam cup? Because it insulates your hand from the hot coffee inside, right? If you try to drink it out of a plastic cup, if the plastic cup doesn't melt, at the very least your hand's going to be really hot. So the styrofoam cup helps to insulate. So usually we use 2 nested foam cups. It's open to the atmosphere. Sometimes we'll put some sort of a lid, a cork, or a piece of cardboard even, just to help insulate. But that is not tight fitting. It's not an airtight situation. So it's open to the atmosphere, therefore the pressure will be constant. And so we can use and we can calculate the change in enthalpy for the reaction, the heat of the reaction. So the calorimeter is going to usually contain water. And so there's a solution inside. So the heat absorbed by the solution is going to equal the mass of the solution times the specific heat capacity for the solution times the change in temperature. This is what we learned yesterday. Q equals MCAT, right? Well, the heat given off by the reaction has to be absorbed by the solution. So at constant pressure, the enthalpy change, or the enthalpy of reaction, is equal to Q at constant pressure, which is Q for the reaction. So we can calculate the heat of reaction by looking at the temperature change of the liquid inside this calorimeter when the reaction occurs. And this is very practical and very, very doable. Now, if we want the heat of reaction per mole, then we need to know how many moles of whatever thing we're interested in reacted, and we just take that heat of reaction that we calculate and we divide by the number of moles. So here's an example. The addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to the following reaction. When 50 milliliters of 0.100 molar silver nitrate is combined with 50 milliliters of 0.1 molar HCl in a coffee cup calorimeter, the temperature changes from 23.40 degrees Celsius to 24.21 degrees Celsius. Calculate the heat of reaction for the reaction as written. Use 1 gram per milliliter as the density of the solution, and the specific heat of water, which is 4.18 joules per gram degree Celsius, as the specific heat capacity. Wow, right? This is just lots of words, lots of numbers, okay? I would say most students would find this challenging. And it does require some thought. Well, let's think about it. Let's draw some pictures. Just pictures can be helpful. That wasn't a picture. So up here, I've got my coffee cup calorimeter, okay, and I've got liquid in here. So what's in here? Well, I've got 50 milliliters of 0.100 molar silver nitrate, and I've got 50 milliliters of 0.100 molar HCl. Okay, that's the liquid in here. We're told the temperature changes from 23.4 to 24.21. So if you see the word calorimeter, the equation should pop into your head, Q equals MC delta T. We're going to need a delta T. Let's calculate delta T. So delta T is the final temperature minus the initial temperature. So the final temperature is 24.21 minus the initial temperature of 23.40. And so the change in temperature is 0.81 degrees Celsius. Everybody with me so far? Okay, so this solution is mostly water, and it's got some silver nitrate in it, and it's got some HCl in it. And so what we do is we use the specific heat capacity of water as the specific heat capacity of this solution. Because it is mostly water, And the fact that it has these ions in it doesn't really change it much at all. So let's think about that equation, right? We're going to need Q equals MC delta T. We have the change in temperature for the solution, right? So what we can do is we can calculate the heat that's absorbed by the solution from this reaction. We know that it's absorbing heat because the temperature went up, right? So we need the mass of the solution and the specific heat capacity of the solution and the change in temperature. Well, we calculated the change in temperature up here. We were told what the specific heat capacity is. We need to figure out what the mass is. How do we do that?
The mass of the different parts or of the solution?
We need the mass of the solution. Why did they give us the density? Why did they say use 1.00 grams per milliliter as the density of the solution? Could we use that to calculate the mass of the solution? Because we can look at the volume of this and the concentration, and we could calculate the mass of silver nitrate, and that's probably where a lot of your minds are going, which is understandable. But that's not what we want. That doesn't include the mass of the water, and most of it's water. We want to know the mass of the solution. And so what we need for that is the density. We're going to use the density. What's the volume of that solution? 100 milliliters. Because we got 50 of this one and 50 of that one, and they're mixed together. So our volume, let's do that over here. We have a volume of our solution is equal to 100.0 milliliters. The density of our solution, we're told to use 1.00 grams per milliliter. Well, if we take 100 milliliters and we multiply by 1 gram per milliliter, we end up with 100 grams. Now, significant figures. If you can't tell, I actually like significant figures. Here 1.00, we're using this density that has 3 sig figs. This developed 4 sig figs when we added these two things together because of the rules for adding. But now this, you can't really see that, there's a decimal point there. This 100 grams has 3 significant figures. That's our mass. That's the mass of the solution. So to calculate Q for the solution, we need the mass of the solution, the specific heat capacity of the solution, the change in temperature of the solution. So we've got 100 grams times 4.18 joules per gram degrees Celsius times our change in temperature so I turned it off. 100 times 4.18 times 0.81 . So this equals 338.58. Let's look at our units. Grams cancel grams, degrees Celsius cancel, and so this has a unit of joules. How many sig figs should that have? 2, because of the change in temperature. So this is that uncertain digit, the last significant figure. Okay, so we calculated something. Is this our final answer? No. So I need to make some space. So I'm going to erase part of this problem. We're done with this stuff up here. So we're looking for heat of reaction, delta H reaction. The heat of reaction is the heat at constant pressure, which is going to be, well, let's do it this way. So the heat Q for the reaction, which is going to equal negative Q for the solution. Because the heat given off by the reaction, the heat absorbed by the solution have the same magnitude, the same number. The only thing that's different is the sign. Their signs are opposite. Okay? So what we calculated down here was the heat absorbed by the solution. That means that the reaction lost 338, right? So up here, the heat of reaction is minus 338.58 joules. We're still not quite done though, because this, remember, delta H is an extrinsic property. It depends on the amount. If we had twice as much of each of these solutions, it would generate twice as much heat. And so this is specifically asking for heat of reaction for the reaction as written, meaning 1 mole of silver nitrate, 1 mole of HCl. So what we need to do is we need to take this quantity and divide it by the moles of one of these so that we get per mole. How many moles of silver nitrate are in that cup? Well, we've got 50 milliliters. Let's convert that to liters. 50 milliliters or 0.0500 milliliters times 0.100 moles silver nitrate per liter. So that should be 0.005, right? Really shouldn't trust my head. 0.005, 00 moles of the silver nitrate. And that's just using the molarity as a conversion factor. I want more space. I'm going to keep the reaction there, but so delta H of reaction for that equation as written is minus 338.58 joules. Well, yeah, I said 8. I didn't write it. 338. That's better. 0.58 joules divided by 0.00500 moles. Divided by 0.005. So now I've got minus 67716 joules per mole. And as written, this is 1 mole. So this is joules per 1 mole of that. But we're only supposed to have 2 significant figures, right? So we could either put this in scientific notation, or we could use kilojoules instead. Which one should we do? Let's use kilojoules. So if we turn this into kilojoules, I'm going to have to make a little space here. If we turn this into kilojoules, that's like that's 1,000. So we need to factor 1,000 out, and so then that's 67.716 kilojoules. A kilojoule is a bigger unit, and so that makes the number smaller. So this is going to be minus 68 kilojoules per mole. Any questions? These problems can be challenging. But one of the things that you're supposed to learn in college, and especially in a more rigorous science class, and this is a majors level chemistry class, is you're supposed to learn how to think. And so you don't just learn how to do things that someone has taught you how to do by rote. You understand concepts, and you've learned general processes, and you learn how to put them all together to solve a problem. Problem solving is a skill that is very useful in real life. And learning how to solve these types of problems, believe it or not, actually carries over into learning how to solve problems in real life, because not all problems are simple and straightforward like 2 plus 2. Any questions? Yes?
So when we had the negative 338 joules,
We
divided by the moles of each substance, is that energy distributed equally among each, or is it shared? How's that working? Because then I think if we had 2 moles of this and then 3 moles of that, how would that change?
That's a good question. In this particular example, notice we have the same number of moles of silver nitrate and HCl, right? Because it's the same volume of the same concentration, and in the balanced equation, it's 1 mole of this and 1 mole of that. If the stoichiometry was different here, if this was 2 and that was 1, yeah, then we'd have to do some extra thinking about that. I mean, then you'd have to think about limiting reactants on top of everything else. And we're not going to make you do that.
We're mastering chemistry?
I don't believe so. No, I don't believe so.
So if it did, we would use the molar value of the limiting reactant.
Yes. If your amounts were not stoichiometric, if it was not the correct ratio of moles of each of these, you'd have to use whichever one was the limiting reactant. Because once the limiting reactant is used up, like let's just say there was excess HCl. Once the silver nitrate is gone, the reaction stops. And the fact that there's extra of the other reagent present really doesn't matter at all. Like if this was 0.2 molar, so the volume was the same of the whole solution, but we had twice as much HCl, this number would still be the same. Because that extra HCl did not react. It just sat around. Okay, that's a very good question. Did I answer it?
Yeah, I'm still trying to understand one thing, though, on the final joules, or the original joules that we had. That is a combined heat of the complete reaction, correct?
That's the heat of the reaction. When this reaction occurs, this is how much heat is given off.
With that much.
Yeah, this is specific for these quantities. And this, what we calculated as our final answer, relates to this equation, the molar amounts in this equation. And if it's not, you would not see this number, as a reference in a textbook or something, because that pertains to this one particular thing, and it's not very useful. A lot of times you'll see delta H is this, minus 68 kilojoules. Well, actually, I can write it in here. You'll see this, delta H RXN equals minus 68 kilojoules. And it won't say per mole when it's written next to the equation. By convention, we understand that if the heat of reaction is given with the balanced chemical equation, that this is for the molar amount specified in the equation.
So then that's per kilo. So that's per mole. So
That's per.
You have that, you have the equation, all you just figure out how many moles you have. And you have
Exactly. Yeah.
Okay.
And so, with stuff like this, we can calculate, like if we were burning, 5 million tons of fossil fuels or something, how much heat is given off. We could calculate things like that. And so, very useful calculations. Any other questions?
It's negative because it's an endothermic, so it keeps...
It's negative because it's exothermic.
Yeah, because it's going to a higher temperature. So
The system here is the silver nitrate and the HCl. Now, they are dissolved in water, but the water is not part of the reaction. The water is part of the surroundings. The temperature of the water went up. Where did that energy come from? It came from the potential energy stored in the chemical bonds of these two chemicals. When they react, they release energy. Exothermic reaction, the energy goes into the surrounding water and the temperature of the water goes up. Yeah, it's the silver nitrate and the HCl are giving money away. And the water's like, hey, great, free money, right? So, especially with all the signs and the exothermic, endothermic, I really think the only way to keep all of this straight is to be able to think about it, like how I just answered her question. Just, talk it through in your head. And sometimes it's helpful to actually just say it all out loud, because I don't know about you, but when I think, my thoughts kind of get jumbled and they go off and, squirrel, and you get distracted and what was I saying? And somehow if you say it out loud, even if there's nobody listening to you, it's easier to keep your thoughts in line. It helps you control your brain a little more. So that can be really helpful. And, explaining a concept to another student is helpful for the student who's not understanding, but it's also helpful for you because when you explain things to people, it helps you to understand it better because it forces you to organize your thoughts. And that's why I encourage you to talk to each other during lab and explain things to each other. And it's good to study together. Okay, any other questions?
So you just found the mole of the silver nitrate, not the HCl?
I could have done either.
Okay.
Yep, I could have done either.
Okay.
And if you look at these, you realize it's the same, right? So I could have divided by moles of HCl. It would have ended up the same.
You don't need both.
I don't need to do both, no. Because it's this many per mole of this, and per mole of that, and per mole of this, and per mole of that.
Okay.
Any other questions?